SwayamPrabha. Digital India. Educated India.
Okay, so we will talk about LFSR based StreamCipher. So, we have seen the LFSR as a key stream generator or pseudo random bit generator. So, let us start with say L bit LFSR. How we define the L bit LFSR? So, it is basically L bit register. We have L flip flop. So, L bits. So, S0, S1, S2 like this. So, dot SL minus 1. Okay, SL minus 1. So, this is we have L bit register. Now, each of these we have a AND gate along with some value, say C0, and this is taking this. So, this is C1 like this. So, if this is SI, then we have a SI is going, and we have CI. These CIs are either 0 or 1 like this. So, this is basically CL minus 1. So, these are all XOR dot XOR with this, and this is coming out. So, this is a typical L bit LFSR. So, these are L bit flip flops, L bit register, and these are these we call state. This is the first 0 state, 1 state like this. So, this is a state. So, now these CIs are either 0 or 1. If the CIs is 0, then whatever the value over here, it will not contribute there. So, that corresponding bit is not contributing in the feedback. If the CIs is 1, then it will contribute it in the feedback, and this will corresponding to a polynomial Px is equal to 1 plus C0x plus C1 x square up to Cl minus 1 x to the power L. So, this is a L degree polynomial. So, depending on the value of CIs, we have this polynomial. So, let us take an example of 4 bit LFSR. So, for 4 bit, we have 4 bit register 1, 2, 3, 4, and we have connections there. So, say we have a connection over here and we have a connection over here. So, this is one LFSR, this is going out, this is one LFSR. So, this LFSR is corresponding to the polynomial 1 plus x. So, this corresponding C0 is 1, C1 is 0, C2 is 0, C3 is again 1, because these are the bit contributing in the feedback. So, linear feedback shift register. So, this is corresponding to this polynomial. So, if we have this polynomial, this is basically this connection. Now, if we have say this polynomial 1 plus x square plus x cube. So, this will corresponding to with LFSR. So, this is again 4 bit. So, this is basically x is not there. So, x square x cube. So, these two, and it is. So, this is the LFSR corresponding to this polynomial. So, given a polynomial, we can have a LFSR, and given a LFSR, one can have this polynomial. Okay. So, suppose we take this polynomial. This polynomial is as a particular characteristics. This is a irreducible polynomial. Not only that, it is a primitive polynomial. We will talk about primitive polynomial when we discuss mathematical background of this course. So, if you take this LFSR and if we start with any initial vector. So, actually we initialize this state by the secret key shared between Alice and Bob. So, if we start with any non-zero initial vector, initial key. So, suppose we are, so this is a secret key shared between Alice and Bob, and we want to run this LFSR, and we want to get the key stream. So, if you do so, then what value will be getting? So, in the first run this 0 will come here, 1 will come here, this 1 will come here, this 0 will come here, and this bit will be replaced by XOR with this and this, which is basically 0. So, now this is the current state of the this LFSR. So, we will copy this value over here, and then again we will. So, each clock we are omitting one bit, last bit. So, feedback we are taking the feedback to fill up the this bit. So, now next this will be output, and this will come here, this will come here, this will come here, again this will be this and this XOR. So, this is 1. So, if we continue like this, so in the next clocking this will come here, this will come here, this will come here, this will come here, and XOR will be this, and because this is the current state of the LFSR. So, this in this XOR, bitwise XOR, this is 0. So, in the next 0 will come here, this will come here, this will come here, this 0 will come here, we XOR this and this. So, this is the key stream bit actually. So, this and this 0 again. So, then this is the current state. So, this will come here and this will come here. So, linear feedback shift register. So, we are just shifting this by 1 bit, and we are taking the feedback based on this connection, based on the polynomial. So, this will be coming here, this will be coming here, this 2 is basically 0. Then we have 1 is going there, and we have here this will come here, this will come here, this will come here, and this 2 is 1. So, this is the, so up to this we got so we got like this 0 1 1 0 0 1 up to this. Now, we copy this here because we do not have space here. So, we copy this value over here and we will continue. So, 1 0 0 0. So, this is the current state. Okay. So, now we again run it. In the next clocking, this 0 will come here, and this 0 will come here, this 0 will come here, this 1 will come here, and this XOR, it will give us 1. So, this is next key stream bit is 0, and then we have again we take this out 0 0 1 1, and this will be 1 again, and we continue like this. So, this is again 0. So, now this is 0 will come here, 1 1 1, and this will be again, this is the current state, this will be again 1. So, now we have 1 1 1 1, and now these are all 1s. So, this is the key stream. So, this will be 0 again, and then this 1 1 1, and this 0 will come here, and this 2 will give us a 1 again, and so this will basically another 0 1 1. Now, this is the current state. So, we will just copy here. So, 1 0 1 1. So, again we will run this to get the next key stream. So, this 1 will come here, this 1 will come here, this 0, this 1 will come here, we XOR these 2, this will give us 0, and then 1 will come here, this 0 will come here, 1 will come here, this 0 will come here, this 2 will give us a 1, and then again 0 will be the output, then this 1 0 1, these 2 will give us 1, and then we have again this 1 will go here, this 0 will come here, 1 will come here, this 1 will come here, and this is 0. So, this is the initial state, it is coming back. So, this is a full sequence. So, this is 1 1 0 1. So, this is a period. So, this is a full period, this is a period of length 15. So, after that it will just generate the same key stream, because we are coming back to the original initial internal state, because we started with this state, this was the key. Again if we continue, we will get the same key stream. So, this is one period of the this key stream generator, pseudo random bit generator, and this sequence we have seen in the. So, if you come to this slide, so this sequence we have seen is satisfying. This is the same sequence here, and we seen that this sequence is satisfying all the properties of the Goulomb's postulates. So, this sequence is a good random sequence in the sense of it is satisfying all the tests of the Goulomb postulates, and even we can try for other few tests and it may pass. So, the conclusion is, so LFSR is giving a good sequence. So, LFSR is a good pseudo random bit generator, provided we choose the polynomial to be a good polynomial. So, here polynomial is basically this. So, 4. So, this is we discuss when we talk about mathematics of this course. This is what is called primitive polynomial. Primitive polynomial. So, we will talk about this in details, what is primitive polynomial. So, if we choose a primitive polynomial, then that corresponding LFSR will give us a good sequence of pseudo random bit generator. So, it is good. Now, we will talk about, so this is a StreamCipher, this is a LFSR bit StreamCipher, basically it generates the key stream. Now, if we just consider this, so as a StreamCipher key stream generation, and if we have this connection like this, so we want to see how good this key stream is. So, we know this is a randomness wise it is good, but is there any other linear, is this key stream is linear or non-linear, that we want to talk about. So, suppose we have a 4 bit LFSR, okay. We have a 4 bit LFSR, and suppose we have this C0 and this is a C1 and this is C2, C3, and we have this XOR and this is coming out, this is going out, okay. And this is a 4 bit LFSR, but CIs are either 0 or 1. So, the corresponding polynomial is basically C0 plus 1 plus C0x plus C2x square plus C3x cube, sorry, C0 plus C1x plus C2x square C3x to the power 4, where C1 C2 are basically 0 or 1. So, it depending whether that corresponding bit is participating in the feedback or not. If it is participating in the feedback, that corresponding CI is, if SI corresponding state SI is participating in the feedback, then the corresponding CI is 1, otherwise that CI value is 0. Okay. So, now suppose, so this is the polynomial. Now suppose this is the key is alpha 1, alpha 2, alpha 3, alpha 4, 4 bit key which is shared between Alice and Bob. So, how we are getting key stream from this LFSR? So, we are first loading this alpha 1, alpha 2, alpha 4 as a initial value of this state. Okay. This is you can consider as a state, and each time this state is changing. So, this could be the initial value of this state. Okay. So, now if we just, so key is, our secret key is basically alpha 1, alpha 2, alpha 3, alpha 4, which is shared between Alice and Bob. Now, what will be the key stream? Key stream is, first key stream bit is alpha 4 will be coming out, then so this will be basically alpha 1 will come here, alpha 2 will be come here, alpha 3 will be come here, and this will be basically summation of. So, this is basically C0 summation of C0. C0 alpha summation of. So, this is C0 alpha 1 plus C1 alpha 2 plus C2 alpha 3 plus C4 alpha 4 like this. So, but the next key stream will be alpha 2 alpha 3 alpha 2 alpha 1. So, all the key bit will be first key stream basically, and then next one the alpha 5, basically this is K1 K2, these are the key stream K3 K4. So, K up to K4 we are getting basically the key, the secret key. Then after that, what about K5? K5 is basically this one, which is having this linear form C0 alpha 1 plus C1 alpha 2 plus C2 alpha 3 plus C4 alpha 4. Okay, so this is basically our K4 K5. Now, how to get K6? K6 will be, so this is basically for K6 we have basically what it will be again. So, this will be, so now for K6 what is the status? So, the status is we have a so K5 will come here. So, next one will be, so this is K5 will come here, and still this is then if K5 is here, then this is say alpha 1 and this is alpha 2. Then also then K5 is here only. Then what is K6 then? K6 is basically K5 will be here, and this is alpha 1, alpha 2, alpha 3, only K4 is gone. So, what is K6 then? K6 will be C0 K5 plus C1 alpha 1 plus C2 alpha 2 plus C3 C0 alpha K5 C1 alpha 1 C2 alpha 2 plus C3 alpha 3. Okay. This is the K5. Now, if you convert this into this, if we use this formula, so it will be again something like some D0 alpha 1 plus D1 alpha 2 plus D3 alpha 3 D2 alpha 3 plus D3 alpha 4. 4 will be there, yeah, 4 will be here, 4 is coming from this one. So, this is again a linear function in alphas. Okay. So, these are just a constant, these di's are combination of this ci's basically. So, this is a linear function. So, again K7 also will be written as some W0 alpha 1 plus W1 alpha 2 plus W2 alpha 3 plus W3 alpha 4 like this. So, any key stream is basically, any key in the key stream is basically linear combination of linear function in the secret key stream, secret key. So, this is a linear function. So, this may be dangerous in a sense of, we will talk about algebraic attack later on. So, we can have some equation, linear equation, then one can try to solve that equation and can guess what is the alphas, because if we know some of the key stream. So, this is algebraic attack, we will talk details about that. So, this linearity is having some problem. So, this is a linear function. So, LFSR is, that is why it is called linear feedback sieve register. So, it is a linear function in alpha 1, alpha 2, alpha 3, alpha 4. Okay. So, this has some problem with the attacks like algebraic attack. So, we will talk about those later on. So, now question is how we can make it non-linear. So, we want to use a LFSR, we want to use LFSR, but we want to make it a non-linear key stream generator. So, this is a linear key stream generator. So, if you just use the LFSR, so LFSR is a linear key stream generator. So, we want to make it non-linear key stream generator. So, idea is to have a non-linear function. So, suppose we have say n LFSR. So, this is one 4-bit LFSR L1, we have another 4-bit LFSR L2, like this. Suppose we have, this is one example how we can use LFSR to make a nonlinear function, nonlinear key stream generator. So, we suppose we have 4-bit 4 LFSR. So, each is coming from a polynomial. So, once we have a polynomial, so basically we have a 4 polynomial and corresponding to each polynomial we have a LFSR. Now, what we do? We just take the output of this LFSR and we have a function which is a nonlinear function. So, say this output say x1 and this output say x2, this output say x3 and this output say x4. It could be instead of 4 it could be 5, 6, n. In general this is a n LFSR of L bit. So, each is giving output key stream. So, this is linear, but this is also each of output of this LFSR is giving linear, but here f we use as a nonlinear function. So, f is a nonlinear function. Okay. So, f is basically nonlinear function. So, this is basically nonlinear key stream bit. So, f could be say if it is 4-bit x1, x2, x3, x4. So, it could be x1 XOR with x1 into x2, XOR with x1, x2, x3, any nonlinear function like this, x2, x4, any nonlinear function we can have use to make it a nonlinear key stream bit generator. So, this could be extended up to n LFSR. So, and each could be a L bit. So, we have basically L degree n polynomial and each is giving us a 1 bit, and this f is the taking this n bit and giving a output bit, and which is a nonlinear function. Okay. So, we can take an example of such LFSR which is basically Griffey generator. So, it is basically based on 3 LFSR. So, this is one example of nonlinear key stream generator based on the LFSR. We can use LFSR, but we have to apply a nonlinear function f. So, here the nonlinear function is basically, here we are having 3 LFSR L1, L2, L3 of any bit. So, this is giving us x1, this is x2. So, this is f is the nonlinear function, this is x3. So, this is one LFSR, this is okay, this is maybe L bit. So, what we do, how we get initialize this? We can initialize this by the secret key which is shared between Alice and Bob. So, we will just put this secret key as the initial value of this state, okay, and then we will run this LFSR, and once we run the LFSR we will get output, this is x1 and this is the x2 output from this LFSR, this is x3. So, this function for Griffey generator is basically of this form x1 x2, this is the AND, then x1 plus x2 into x3. So, this is basically x1 x2, then x2 x3 XOR x3. So, this is a nonlinear function. So, this will generate the nonlinear key stream bits, okay, which is not linear. So, we can just draw this in a logical way. So, this is x1. So, x1 is ANDing with x2. So, this is x2, this is x1, this is x2, x1 is ending with x2, and then this x2 is also having a negation. So, and this we are ending with x3, this we are ending with x3, and these two will we are just doing the XORing, bitwise XORing, and it is giving us the key stream. Okay. So, this key stream is a nonlinear key stream, because we are using the nonlinear function f like this. So, this is one example where we can use the LFSR. LFSR is basically a linear key stream generator, but we can use LFSR as many as we want, and we just initialize this internal state as the secret key shared between Alice and Bob, and then each of this LFSR we just initialize by that key, and then we run this, and each time it is giving output that x1, x2, x3, and then we take a nonlinear function f to make it nonlinear key stream generator. Okay. So, this is the example where we can use LFSR as a nonlinear LFSR to generate a nonlinear key stream, although LFSR is a linear. Now, we talk about the general form of the StreamCipher. General structure of a StreamCipher, in particular synchronized StreamCipher. It is called synchronized StreamCipher. Synchronous StreamCipher. Synchronous StreamCipher means the key stream will only depend on the secret key shared between Alice and Bob. So, key stream will not depend on the plain text or ciphertext. So, we are not taking any feedback of the plain text or the ciphertext. So, it is independent of the plain text and ciphertext. So, that StreamCipher is called synchronized StreamCipher. Another type of StreamCipher is asynchronized StreamCipher, where we will give the another input as a plain text or the ciphertext bit. So, for synchronized, the key stream is independent of plain text and the ciphertext. So, we are not having any input of the plain text or ciphertext in the key stream. So, the StreamCipher we have seen, LFSR based StreamCipher, all are synchronized StreamCipher, because it is just taking the original key and it is giving us the key stream. So, one example of a synchronized StreamCipher is LFSR based StreamCipher we have seen. Okay. So, now we can write a general structure of a synchronized StreamCipher. So, it has basically having a state which we denote by ST. For example, if it is LFSR, then if it is 4 bit, so this state is basically 4 bit register, and which is updating by a state update function. The state is every time updating, like for LFSR we have linear feedback shift register, linear feedback shifting. So, that is our G. So, this way we are updating this state, and this state is initialized by the secret key shared between Alice and Bob, and then we are having another function H, which is taking the content of the state and which is giving us the key stream. So, this is K1, K2 like this, Ki. So, this is the key stream, this is the pseudo random bit generator, key stream. So, this is, and then we XOR with this with the plain text bit to get the ciphertext bit C1, C2, Ci so far. Okay. So, this is the at tth time, this is the state. So, which is initialized by the secret key, and every time we are updating the state by the G function, and every time we are taking the content of the state and we are applying this function H, we are getting the key stream, the dieth key stream. So, like this. So, LFSR is one example of the synchronized StreamCipher. So, this is the general form and then construction of a synchronized StreamCipher. Thank you.